Dora, Weight-Decomposed Low-Rank Adaptation. Among the widely used parameter-efficient fine-tuning methods, LoRA and its variants have gained considerable popularity due to avoiding additional inference costs. However, there often exists an accuracy gap between these methods and full fine-tuning. In this work, we first introduce a novel weight decomposition analysis to investigate the inherent differences between full fine-tuning and LoRA. Aiming to resemble the learning capacity of full fine-tuning from the findings, we propose weight-decomposed low-rank adaptation, or Dora. Dora composes the pre-trained weight into two components, magnitude and direction, for fine-tuning. It specifically employs LoRA for directional updates to efficiently minimize the number of trainable parameters. By employing Dora, we enhance both the learning capacity and training stability of LoRA, while avoiding any additional inference overhead. Dora consistently outperforms LoRA on fine-tuning LLaMA, and VL-BART on various downstream tasks, such as commonsense reasoning, visual instruction tuning, and image-video-text understanding. Introduction. Pre-trained models with extensive general domain data sets have demonstrated remarkable generalization abilities, significantly benefiting a wide array of applications. To tailor these general models for specific downstream tasks, full fine-tuning is commonly employed, involving the retraining of all model parameters. However, as the size of models and datasets expands, the expense associated with fine-tuning the entire model becomes prohibitively large. To address this issue, parameter-efficient fine-tuning methods have been introduced to fine-tune the pre-trained models with only a minimal number of parameters. Among these, LoRA, which does not change the model architecture, has become notably popular for its simplicity and efficacy. Nevertheless, there is still a capacity gap between LoRA and full fine-tuning, which is often attributed to the limited number of trainable parameters, without further exploration of other underlying causes. Drawing on weight normalization, which achieves faster convergence by improving the conditioning of the gradient with weight reparameterization, we introduce a novel weight decomposition analysis. This analysis initially reparameterizes model weights into magnitude and directional components, and subsequently examines the changes in magnitude and direction introduced by LoRA and full fine-tuning. Our analysis reveals that LoRA and full fine-tuning exhibit markedly distinct patterns of updates, leading us to surmise that these variations mirror the learning capability of each method. Inspired by our findings, we propose weight-decomposed low-rank adaptation, or Dora. Dora begins by decomposing the pre-trained weight into its magnitude and directional components, then fine-tunes both. Given the substantial size of the directional component in terms of parameters, we exploit LoRA for the directional adaptation to enable efficient fine-tuning. By showing a learning behavior similar to full fine-tuning both empirically and mathematically, suggesting a learning capacity closely resembling full fine-tuning, we have validated Dora across a wide variety of tasks, from natural language processing to vision language, and over various backbones, including large language models, and vision language models. The experimental results show that Dora consistently outperforms LoRA without sacrificing inference efficiency. The summary of our contributions is as follows. We introduced Dora, a novel parameter-efficient fine-tuning method that incorporates weight decomposition, achieving a learning capacity closely resembling full fine-tuning without any additional inference latency over LoRA. We introduce a novel weight decomposition analysis to uncover the fundamental differences in the learning patterns of full fine-tuning and different parameter-efficient fine-tuning methods. Dora consistently surpasses LoRA on various tasks, from natural language processing to vision language benchmarks, and across various backbones, including large language models and vision language models. Related works. Parameter-efficient fine-tuning methods are designed to reduce the high expense of fine-tuning large-scale models. They achieve this by training a relatively small subset of parameters compared to the total number of parameters for adapting to downstream tasks. Existing parameter-efficient fine-tuning methods can be divided into three categories. Adapter-based methods involve introducing additional trainable modules into the original frozen backbone. Prompt-based methods add extra soft tokens to the initial input and focus solely on fine-tuning these trainable vectors. LoRA and its variants apply low-rank matrices to approximate weight changes during fine-tuning and can merge with pre-trained weights prior to inference. Our research also falls within this third category, and we validate the efficacy of our proposed method alongside LoRA and its variants through comprehensive experimentation. Pattern analysis of LoRA and full fine-tuning. Low-rank adaptation LoRA. LoRA proposes using the product of two low-rank matrices to update the pre-trained weights incrementally. For a pre-trained weight matrix, LoRA models the weight update utilizing a low-rank decomposition. Consequently, the fine-tuned weight can be represented as the sum of the pre-trained weight and the weight update. The pre-trained weight remains static during the fine-tuning process, and the parameters are being trained. Notably, this decomposition of the weight update can be substituted with other LoRA variants. Additionally, we can merge the learned weight update with the pre-trained weight before deployment, and given that both the fine-tuned weight and the pre-trained weight fall within the same dimensionality, LoRA and its related variants do not introduce any extra latency during inference compared to the original model. Weight-Decomposition analysis. The study presented in LoRA suggests that LoRA can be considered a general approximation of full fine-tuning. By gradually increasing the rank of LoRA to align with the rank of pre-trained weights, LoRA can attain a level of expressiveness akin to that of full fine-tuning. Consequently, many previous studies have attributed the discrepancy in accuracy between LoRA and full fine-tuning primarily to the limited number of trainable parameters, often without further analysis. Drawing inspiration from weight normalization, which reparameterizes the weight matrix into magnitude and direction for accelerating optimization, we introduce an innovative weight decomposition analysis. Our analysis restructures the weight matrix into two separate components, magnitude and direction, to reveal the inherent differences in LoRA and full fine-tuning learning patterns. Analysis method. This analysis examines the updates in both magnitude and direction of the LoRA and full fine-tuning weights relative to the pre-trained weights to reveal the fundamental differences in the learning behaviors of both. The weight decomposition ensures that each column of the directional matrix remains a unit vector, and the corresponding scalar in the magnitude vector defines the magnitude of each vector. For our weight decomposition analysis, we select the VL-BART model, fine-tuned on 4 image text tasks for a case study. We decompose the pre-trained weight, the full fine-tuned weight, and the merged LoRA weight of the query value weight matrix. We perform weight decomposition analysis on each of these checkpoints to determine the magnitude and direction differences throughout different layers. Analysis results. LoRA exhibits a consistent positive slope trend across all the intermediate steps, signifying a proportional relationship between the changes in direction and magnitude. In contrast, full fine-tuning displays a more varied learning pattern with a relatively negative slope. This distinction between full fine-tuning and LoRA likely mirrors their respective learning capability. While LoRA tends to either increase or decrease the magnitude and direction updates proportionally, it lacks the nuanced capability for more subtle adjustments. Specifically, LoRA does not show proficiency in executing slight directional changes alongside more significant magnitude alterations, or vice versa, a feature more characteristic of the full fine-tuning method. We suspect that such a limitation of LoRA might stem from the challenge of concurrently learning both magnitude and directional adaptation, which could be overly complex for LoRA. Consequently, in this work, we aim to propose a variant of LoRA that exhibits a learning pattern more closely resembling that of full fine-tuning and can improve the learning capacity over LoRA. Method was Weight-Decomposed Low-Rank Adaptation. Drawing from the insights of our weight decomposition analysis, we introduce weight-decomposed low-rank adaptation, or Dora. Dora initially decomposes the pre-trained weight into its magnitude and directional components and fine-tunes both of them. Because the directional component is large in terms of parameter numbers, we further decompose it with LoRA for efficient fine-tuning. Our intuitions are twofold. Firstly, we believe that limiting LoRA to concentrate exclusively on directional adaptation, while also allowing the magnitude component to be tunable, simplifies the task compared to the original approach where LoRA is required to learn adjustments in both magnitude and direction. Secondly, the process of optimizing directional updates is made more stable through weight decomposition, which we delve into more thoroughly in the next section. We initialize Dora with pre-trained weight, where the magnitude is set to the vector-wise norm of the pre-trained weight, and the direction is set to the pre-trained weight. We then keep the direction frozen and the magnitude a trainable vector. The directional component is then updated through LoRA. Dora can be formulated as the sum of the product of the magnitude and the normalized pre-trained weight and the weight update, normalized by the vector-wise norm of the sum. The incremental directional update is learned by multiplying two low-rank matrices. The matrices are initialized in line with LoRa's strategy to ensure that the fine-tuned weight equals the pre-trained weight before the fine-tuning. Furthermore, Dora can be merged with the pre-trained weight before inference, thereby not introducing any additional latency. Gradient analysis of Dora. We first derive the gradient of Dora and illustrate how our proposed decomposition benefits the optimization of the incremental directional update. Subsequently, we analyze from the gradient's perspective to explain the learning pattern of Dora, which tends to have a negative slope. The gradient of the loss with respect to the directional update is scaled by the magnitude divided by the vector-wise norm of the updated direction and is projected away from the current weight matrix. These two effects contribute to aligning the gradient's covariance matrix more closely with the identity matrix, which is advantageous for optimization. Given that the directional update is the difference between the updated direction and the initial direction, the optimization benefits derived from this decomposition are fully transferred to the incremental directional update, enhancing the learning stability of LoRA. We can gain further insight into the learning pattern of Dora by considering two hypothetical update scenarios. One involves a smaller directional update while the other involves a larger one, with both having the same norm. The smaller directional update tends to have larger magnitude updates, while the larger directional update tends to have smaller magnitude updates. This conclusion generally holds in practice, as evidenced by our experimental results. Reduction of training overhead. To address the additional memory required during backpropagation, due to the divergence in the gradient of the low-rank updates from the gradient of the fine-tuned weight, we suggest treating the vector-wise norm of the updated direction as a constant, thereby detaching it from the gradient graph. This means that while the norm dynamically reflects the updates of the incremental directional update, it won't receive any gradient during backpropagation. This approach reduces the gradient graph memory consumption drastically without a noticeable difference in accuracy. We conduct an ablation study to evaluate the impact of the proposed modification on fine-tuning LLaMA 7B and VL-BART. The results indicate that the modification leads to a training memory reduction of approximately 24.4% in fine-tuning LLaMA and 12.4% in VL-BART. Furthermore, the accuracy of Dora with the modification remains unchanged for VL-BART and shows a negligible difference of only 0.2 compared to Dora without the modification on LLaMA. Consequently, all subsequent experiments with Dora incorporate this adjustment. Experiments. We conduct a variety of experiments to showcase the efficacy of Dora on various tasks including language, image, and video domains. Firstly, we evaluate Dora against several parameter-efficient fine-tuning methods by fine-tuning LLaMA 7B, 13B, Yamato 7B, and LLaMA 3.8BB on common-sense reasoning tasks. Subsequently, we extend from single modality to multimodality. We compare Dora with LoRA across multitask image, video text understanding tasks, using VL-BART and visual instruction tuning with LLaVA 1.57b. Following this, we explore the compatibility of Dora with LoRA and VRA for instruction tuning on LLaMA 7b and LLaMA 7b. Furthermore, we perform a series of ablation studies to illustrate that Dora surpasses LoRA in performance, irrespective of the number of fine-tuning training samples and rank variations. Lastly, we analyze the tuning granularity of Dora and show that Dora can achieve better accuracy than LoRA with fewer trainable parameters by selectively updating only the directional components of certain modules. Common sense reasoning. We evaluate Dora against LoRA and several baseline methods on LLaMA 7B, 13B for common sense reasoning tasks. We also include ChatGPT's accuracy obtained with GPT 3.5 Turbo API using a zero-shot chain of thought. The common sense reasoning tasks comprise 8 subtasks, each with a predefined training and testing set. We amalgamate the training datasets from all 8 tasks to create the final training dataset and conduct evaluations on the individual testing dataset for each task. To ensure a fair comparison, we initially fine-tuned models with Dora following the LoRA configuration, maintaining the same rank while adjusting only the learning rate. Then, we further have the rank used in Dora compared to LoRA and denote this adjusted configuration as Dora. The results demonstrate that Dora consistently surpasses all baseline methods across both LLaMA 7B, 13B, Yamato 7B, and LLaMA 3.8B. Notably, in the LLaMA 7B model, where LoRA exceeds the performance of other baselines, Dora further enhances accuracy, outstripping ChatGPT's accuracy levels. Conversely, for LLaMA 13B, where LoRA's effectiveness is inferior to the parallel adapter, Dora achieves superior accuracy over LoRA and comparable accuracy to the parallel adapter, with only a quarter of the trainable parameters required by the parallel adapter and without adding any extra inference overhead. Additionally, Dora consistently surpasses LoRA on both Yamato 7B and LLaMA 3.8BB. Furthermore, Dora exceeds LoRA's performance despite having only half as many trainable parameters as LoRA. Image, video text understanding. Having shown that Dora can consistently achieve better accuracy on fine-tuning large language models, we would like to see if Dora can remain competitive on multimodality fine-tuning tasks. We compare Dora with LoRA and full fine-tuning on VL-BART across 4 different image text tasks and 4 different video text tasks. We follow the same framework as previous work and fine-tune VL-BART within a multitask framework for both image video text tasks. We adopt the same setup as that of LoRA outlined in previous work when applying Dora. The results show that Dora uniformly surpasses LoRA in accuracy while maintaining a similar count of trainable parameters. In particular, Dora exceeds LoRA's performance by nearly 1% in image text understanding tasks, reaching the accuracy level of full fine-tuning. Moreover, Dora achieves roughly 2% higher accuracy than LoRA in video text understanding tasks. Visual instruction tuning. We further scale up the model size and compare Dora to LoRA and full fine-tuning on the visual instruction tuning tasks with LLaVA 1.57b. The training datasets contain several datasets from visual question answering, optical character recognition, region-level visual question answering, visual conversation and language conversation data. We follow the same configuration as the LoRA configuration provided by previous work. The results indicate that the average accuracy of LoRA already surpasses full fine-tuning, which could imply that full fine-tuning might be experiencing issues with overfitting. Given that Dora is designed to enhance LoRa's performance to more closely resemble that of full fine-tuning, in scenarios where full fine-tuning is inferior to LoRA, Dora's improvement over LoRA might not be as pronounced as observed in other experiments. Nonetheless, Dora still demonstrates superior performance over both LoRA and full fine-tuning. Compatibility of Dora with other LoRA variants. To explore Dora's compatibility with other LoRA variants, we select Vera as a case study. Vera suggests freezing a unique pair of random low-rank matrices to be shared across all layers, employing only minimal layer-specific trainable scaling vectors to capture each layer's incremental updates. This approach allows Vera to reduce trainable parameters significantly compared to LoRA, with only a minimal impact on accuracy. We apply Vera for the directional update in Dora, and name such a combination Devora.do. We assess the effectiveness of both Devora and Dora compared to Vera and LoRA across LLaMA 7b and LLaMA 7b, focusing on instruction tuning with the cleaned alpaca dataset. The performance of the fine-tuned models is then evaluated on the MT-Bench benchmark by generating model responses to a predefined set of multi-turn questions. These responses are then evaluated by GPT-4, which reviews each answer and assigns a numerical score. The results demonstrate that our proposed method exhibits consistent improvements over Vera and LoRA for both LLaMA 7b and LLaMA 7b BART. This effectively showcases the compatibility of Dora with Vera. In particular, Devora merges the advantageous qualities of Dora and Vera, attaining scores that are on par with or even surpass those of LoRA, yet with significantly fewer parameters. To further assess Dora's ability to remain competitive under varying amounts of training data, we compare Dora to LoRA and Devora, to Vera for fine-tuning LLaMA 7b, LLaMA 7b, with a range of instruction tuning sample sizes. The results show that Dora and Devora consistently outperform LoRA and Vera across all training sample sizes. Robustness of Dora towards different rank settings. We explore the impact of various rank configurations on Dora and LoRA by adjusting the rank within a set of values and assessing the performance of the fine-tuned LLaMA 7b on common-sense reasoning tasks. The results show that Dora consistently surpasses LoRA across all rank configurations, with the performance gap widening for lower ranks. This demonstrates that Dora retains resilience and consistently superior performance over LoRA, regardless of the rank setting. Tuning granularity analysis. Given the observation that significant changes in magnitude often result in relatively smaller directional changes, we investigate whether it is possible to decrease the number of trainable parameters by updating only the magnitude components of specific modules, while continuing to update both the magnitude and directional components for the remaining linear module. Our findings indicate that Dora can achieve superior accuracy by updating only the directional and magnitude components of certain modules, while updating both the magnitude and direction for the rest, using fewer trainable parameters than LoRA. Broader impacts. Dora enhancements to LoRA. While fine-tuning large language models with parameter-efficient fine-tuning significantly reduces training memory overhead, a considerable amount of GPU memory is still required to initially load the model weights onto the GPUs to further decrease the memory demands of fine-tuning. LoRA suggests quantizing the pre-trained model to 4-bit and fine-tuning LoRA on top of the frozen low-bit backbone. With Dora, which narrows the gap between LoRA and full fine-tuning, it is natural to also explore whether Dora can enhance the accuracy of LoRA within the LoRA framework. Recent work substitutes the LoRA component in LoRA with Dora, dubbing it Dora, and incorporates the training pipeline with fully sharded data parallel to enable model splitting and parallel training across multiple GPUs. Experiments on fine-tuning LLaMA 7b, LLaMA 8b. Using the Orca math dataset with Dora, LLaMA, and full fine-tuning show that Dora not only significantly surpasses LLaMA, but also slightly outperforms full fine-tuning on both models while using considerably less memory. This indicates that Dora can effectively combine the parameter efficiency of LLaMA with the more granular optimization of full fine-tuning. Text-to-image generation. As diffusion models have expanded in size, LoRA has become a popular method for efficiently fine-tuning large stable diffusion models. We explore whether Dora's advantages over LoRA extend to the task of text-to-image generation. Following the training pipeline of DreamBooth for fine-tuning SDXL, the results indicate that Dora achieves significantly better personalization than LoRA when using the same training settings and more accurately reflects the training targets. Conclusion. In this work, we first conduct a novel weight decomposition analysis to reveal the distinct learning patterns between LoRA and full fine-tuning. Building on these insights, we introduce Dora, a fine-tuning method that is compatible with LoRA and its variants and exhibits a closer resemblance to full fine-tuning's learning behavior. Dora consistently outperforms LoRA across various fine-tuning tasks and model architectures. Specifically, Dora improves upon LoRA in commonsense reasoning and visual instruction tuning tasks. Furthermore, Dora also shows compatibility with VL-BART on the alpaca instruction tuning task. Moreover, Dora can be considered a costless alternative to LoRA, as its decomposed magnitude and direction components can be merged back into the pre-trained weight after the training, ensuring that there is no extra inference overhead. For future work, we wish to explore the generalizability of Dora in domains beyond language and vision, particularly in the field of audio. Acknowledgements. We extend our gratitude to Benjamin Bosson, Younes Belkada and Saurabh Mangrulkar from Hugging Face for their assistance in integrating Dora into the PEFT package, thus making our work more accessible to the broader public. We thank Kerem Togatlu, Jonathan Whitaker, and Jeremy Howard from ANSA AI for their work on the implementation and experiments of Dora FSDP, which makes fine-tuning of large language models with Dora on consumer GPUs a lot more feasible. We also thank Sebastian Rashka for his well-written tutorial on Dora, which offers a thorough overview of the background knowledge necessary to comprehend Dora. Impact Statement. This paper presents work whose goal is to advance the field of machine learning. There are many potential societal consequences of our work, none of which we feel must be specifically highlighted here.